Alright, so in the last video we were talking about these different categories of exoplanets. So we have these hot Jupiters, there's of course cold Jupiters that are further away from their host star, and then of course, which I had already mentioned, these what are called super Earths. That's the super Earths. That's the term that's used. These are anywhere from 2 to about 10 times the mass of the Earth. We haven't found any that are about the size of Earth, and we're always hoping that soon we'll be able to do that. There's just something humanly, I don't know, there's some human desire to find a planet out there that is about the same size as the Earth. Anyhow, so we've these super Earths, we've detected over 700 of them so far. And that number is increasing all the time. All right, so this is another way of measuring the planets, or detecting the planets, and it's called gravitational microlensing. Okay, so let me explain how this works. We've actually known about this, or actually Einstein is the one that predicted this, not about planets, but the fact that a massive object, so let me back up just a little bit. In the early part of the 20th century, so around 1916 or so, Einstein proposed a new theory of gravity. It doesn't make Newton's theory obsolete or anything like that. Newton's theory of gravity works just fine for ordinary objects, but when things get more extreme, Einstein's theory of gravity turns out to work better than Isaac Newton's theory of gravity. So if you look at like one example is like the orbit of Mercury. Using Isaac Newton's theory of gravity, the orbit of Mercury is not quite explained. You can't predict exactly where Mercury is going to be within over the course of one human lifetime, for example. It'll deviate slightly from that. But if you use Einstein's theory of gravity, you can much more accurately predict where Mercury is going to be. So that's one example within our solar system. Of course, other examples are things like black holes. Einstein's theory of gravity explains that is certainly a possibility. All right, so what Einstein's theory of gravity says is that mass itself causes the curvature, the bending, if you will, of space and time immediately around it. So the closer an object is to another massive object, the more gravity is bent. So that even light, in fact, has to be bent by gravity. So if you have, let's say there's some distant star system, and within that star system there is a planet. There's certainly always light from even more distant stars behind that planet. Behind it means, from our perspective, from where we are in the galaxy, there's always stars, right? I mean, it might appear dark in different parts of the sky, but if you have a more and more powerful telescope, you can see that light. So let's go back to that. This planet is going around. Let's even say it's a relatively nearby star system. So this planet is orbiting, its host star, and as it does so, let's say that our telescopes are powerful enough to be able to detect light that is even, of course, further, light from distant stars, not the star that the planet is orbiting, but much more distant stars. What happens is that starlight, as it passes, close to the host star, or even the planet, that star will tend to bend. Sorry, that light will tend to bend. And the amount of bending tells us how much mass is there, according to Einstein's theory of gravity, which, by the way, is called the general theory of relativity. All right, so that's another method, and the conditions have to be just right for us to be able to detect this. There's some nice pictures here that are this picture is showing this kind of thing happening. With the microlensing is, it is detectable with our current technology. It'll be even more detect, more. We'll be able to detect more things, more of these planets using microlensing in the future. As technology gets better and better. All right, so let's see. Measuring exoplanets. We have to, one of the things we want to do is measure the density of these things. So we need to know the mass. Now, the mass of a planet is, if it's a planet, it's going around its host star or host stars. Anytime one object orbits another, you can use what's called the modified version of Kepler's third law to measure its mass. Then you have to determine what the radius of the planet is, and that's much more difficult. That involves. You use the actual transit of the planet, and it's very precise timing of when the light from the host star dims, and then basically imagine as the planet gets right at the edge of the star, the time it takes the starlight to begin to dip, and then dip completely, that gives you what the size of the star is, or the radius of the size of the planet is. And so it's not the most precise way, but it's the best that we have right now, and that'll give us a sense of the size of the star. And so with about roughly more than 500 exoplanets, we can actually measure the radius, which once you can measure the radius, you can you almost always know the mass, right? Because it's in orbit around some star, and so you can measure the mass. With the ones that we can detect the radius, you get a good number, a good reliable number for the radius of these things. You can also measure. It's just a calculation, the mass divided by the volume, and the volume comes from, it's a spherical object, so the volume is 4/3 times pi times the radius cubed, right? And so you can detect, you measure the radius, you can calculate the volume, and then the mass divided by the volume is the density. And then, of course, we compare the density to the density of the planets in our solar system, like for example, the Earth, right? The Earth's density is about 5.5. The density of liquid water is about 1 gram. 5.5 grams per cubic centimeter that's the density of our Earth. Our moon, for example, is a density of about 3.3. Liquid water is 1 gram per cubic centimeter. So with some of these exoplanets, we can measure their densities, and that gives us some sense of what these planets might be made of. This figure compares the super Earths, and where are they in what's called their habitable zone. Okay, so let me go over what the habitable zone is. For different stars, that is different distances. Like if you take the sun, right, our star. The habitable zone is the point where a planet would be far enough from the star so that liquid water can exist, and then close enough to the star that liquid water would right. If it's too close, the liquid water would be vaporized, right? It would just be a gas. If it's too far from the star, the water would no longer be a liquid, it would turn into ice, into a solid. And so the point that happens for our solar system is closer than where the Earth is. The Earth certainly is within the habitable zone of our sun, but no further than about the middle of the asteroid belt. So that's where, that's what's called the habitable zone. And so it's always interesting. And again, that's the habitable zone for our star. Hotter stars, there are stars that are much hotter than the sun, so that habitable zone is going to be at a different location, right? The planet would have to be further away for liquid water to exist. For cooler stars than our sun, the planet would have to be a lot closer for the water to exist in liquid form as opposed to gaseous form. Or, I'm sorry, as opposed to ice. All right, so this is an example of, this is not a real picture of Kepler. And notice it's using, that the designation is, Kepler 186f. So this is a particular planet that was detected by the Kepler spacecraft, and this is just an artist's interpretation of this particular planet. Notice it's a little bigger than the Earth, comparatively. So that would be one of the super Earths. So a big question is our solar system completely different than other solar systems? How different is it? It seems to be quite different, actually. Most of the star systems that we find, the large Jupiter-sized worlds, are relatively close to their host star, certainly within 1 astronomical unit or less. But there are some similarities to our star system, and that gives us at least a sense of, we're on the right track, with the condensation theory of planet formation. So here's one of the similarities is that orbits are relatively isolated and coplanar. That is, all the planets that when we detect planets around a star system, they're all roughly in the same plane. And they all the planets seem to be orbiting in the same direction. And the ones, the systems the planetary systems that we find where we can actually detect debris, disks of material, there are some that have this, and the disk, of course, is that the debris is within the plane of the planetary system. All right, so there's some similarities. Let's see. Is our example of a cold Jupiter, that where Jupiter is at the position that it is within our solar system? Is this really unusual? So we look and we see, systems out there that are completely almost exactly like our system, where there's a planetary system where a Jupiter-sized world is exactly where, the same distance it is from its host star as our Jupiter is from the sun. So that gives us some sense that other solar systems are being we detect other solar systems that are similar to ours, although most of them are not. All right, let's see. Current theories include the possibility. This is a relatively recent theory that these Jupiter-sized worlds have migrated inward due to friction. friction with the solar nebula material